Hello class, my name is Ken, and this video will be going over flow past immersed objects within a fluid. There are two different types of drag, wall drag and form drag. Wall drag, which is shown at the top, happens when there is a force on the solid wall that is touching the fluid in the direction of the flow. This is calculated by multiplying the shear stress of the fluid times the area of the surface. Form drag occurs when there is a surface in the direction of the flow, causing the direction of the flow to change. At the center of the solid that is immersed in the fluid is the stagnation point. The stagnation point is where the velocity of the fluid is zero. The fluid then forms streamlines around the solid and accelerates, then decelerates. This additional force on the fluid movement is the effect of form drag. The weight that is formed in the back of the solid can be minimized with a more streamlined solid because the merging of the streamlines is not as steep. For the drag force in a fluid past immersed solid objects, the drag coefficient is derived similarly to the friction factor in flows through a channel. The drag coefficient, which is shown at the top in the middle, is dimensionless and it equals the ratio of the drag force per unit area over half the density times the free stream velocity squared. This relationship can also be rearranged to solve for the total drag force. The Reynolds number for a given solid within an immersed fluid can also be given as the product of the diameter, velocity, and density all over the viscosity. Thank you, and Conan will take it from here.
Hello guys, my name is Conan and today I'm going to be talking about flow past sphere, long cylinder, and disk. To begin with, it's important to realize that the correlation between the drag coefficient and the Reynolds number depends on various factors such as the geometry of the solid as well as the orientation of the solid with respect to the direction of the flow. In the case of flow past a sphere with a Reynolds number of 1 or less than 1, it has been determined that the experimental drag force is equivalent to the theoretical Stokes law equation, which is provided here. For us, now this equation can be used along with the experimental drag coefficient equation, which was presented in the previous section, to determine the drag coefficient that is predicted by Stokes law, which is also presented here in terms of the Reynolds number, 24 over the Reynolds number. Now, for other cases, this diagram has been developed based on experimental data, and it correlates the Reynolds number and the drag coefficient. Taking a closer look at the diagram, we realize that as the Reynolds number increases from 0 to about 1,000, the drag coefficient will decrease, and this is a similar behavior for all three geometries. For Reynolds number between 1,000 and more or less 200,000, the drag coefficient remains relatively constant, and in the case of a sphere, it's going to be 0.44. At about 300,000 in this region, there is a sudden drop in the drag coefficient, which is basically due to the boundary layer becoming fully turbulent. And after, at a Reynolds number of about 500,000 and above, the drag coefficient becomes constant again, which for the case of a sphere is going to be 0.13, it's going to be 0.33 for a cylinder and 1.12 for a disk. Now, to better illustrate these concepts, we can complete an example together. So we have air at these conditions, and it's flowing past a sphere. These values can be obtained in the appendix of the textbook or in other sources. And we first find the Reynolds number, which is going to be equal to 5.781 times 10 to the fourth power. And having found the Reynolds number, we can go back to the diagram that we just presented and find the drag coefficient to be approximately 0.47. And having found that, then we can use the equation provided in the previous section to determine the drag force, which will be, in our case, 0.1958 units. It's important to realize that we cannot use the equations derived from the theoretical Stokes law for this example, because obviously the Reynolds number is much larger than 1 and it would not be applicable. That will be it for this section, and now my classmate David will take care of the rest. Thank you.
Hello everyone, my name is David and I'll be talking about flow in packed beds, or 3.1c. And a packed bed is just a reactor that's packed with a whole bunch of particles in there, and they act as a catalyst for the reaction that's going to happen in there. And this isn't accurate. Maybe if you go to FSU, you only use this many particles, but in reality, there are a lot more that are in the bed at one time. So let's just go through some parameters that we can define for this new system, because it's not just an empty cylinder. We have this right here, which is the void fraction, okay? And it's the void volume over the total volume of the reactor, okay? And it's unitless because it's volume over volume. Then we have the specific surface, which relates to the particles, and it's just the fraction of the surface area over the volume of the particle, which is important when you're determining how the fluid interacts with each of the particles, okay? And knowing that this void volume is a fraction, we can take 1 minus that here, and we can get the actual volume that is taken up by the particles, okay? And so we can then define the ratio of the total surface area to the total volume of the reactor, and we can find it as this big A here equals our AB here, specific surface, times 1 minus the void volume, okay? And for a sphere, subbing in the formulas for surface area and for volume, you end up getting this relation here, which is 6 over the diameter of each particle times 1 minus the void. All right, so let's move on here. Let's talk about velocity, which is right here. So the velocity of a fluid flowing into an empty cylinder would be known as the superficial velocity, okay? And here, the superficial velocity, it's not exactly accurate, okay? When someone's superficial, they try to be nice on the outside, but on the inside, they're not really a good person. So on the outside, this seems like it's a good expression, but it doesn't account for the fact that we have particles in there. And this void is kind of this void thing here is kind of the correction factor, where we can relate the superficial, not so useful one, with the interstitial velocity, which does account for the fact that there are particles in there, okay? And then now we can talk about our Reynolds number, which has velocity in it. The Reynolds number, as we know, generally is just the density of the fluid times the velocity times the length of the cross-section over the dynamic viscosity. And we can plug in the numbers, or the relations that we have for the velocity, and we get this expression here for the Reynolds number with this simplification of G equals the superficial velocity times the density. All right? Now, let's talk about the hydraulic radius. And this parameter is just a measure of the efficiency of the flow, okay? So, because we want the fluid to interact with each of the particles. So, it measures how much the cross-sectional area of the available flow over the wetted perimeter, so how much it actually goes into contact with the particles, all right? So we have this here, as that relation when we plug everything in and simplify it. And then we also have the diameter, which is 4 times that radius. Now, given all of these parameters, what we can do is we can start with the basic equations for flow in an empty cylinder here and here. This is for laminar flow, and this is for turbulent flow, okay? So after plugging everything in, we go from this equation right here and this equation right here to these two on this side. And then we can combine them, and we have flow for turbulent and laminar flow in a packed bed. And the corrections that we have here, like this 1.75 and this 72 changing to 150 up here, that's just from experimental data. And then we also have this fanning friction factor, which for turbulent flow is constant because it kind of averages out because the fluid is just going crazy. So it just becomes constant and doesn't depend on anything. So now we have the complete equation here for, right here, for laminar and turbulent flow in packed bed. And then John will be taking over from here. Thank you.
Hello, I'm Jonathan, and today I'll be the last lecture talking about fluidization in packed beds. So what is fluidization to begin off? Well, fluidization is when a fluid flows upwards through a packed bed of particles, causing those particles to start to move and act like a fluid themselves. So in order to do the math behind this and figure out all of the intricacies of fluidization, we need to know a couple of variables first. So the first variable is V prime mf, which is basically just the minimum velocity needed for those particles to move. And this velocity is basically the velocity needed to counteract the velocity downwards of the particles due to gravity. And then the next term we have is the porosity, the minimum porosity, which is the minimum porosity needed for fluidization of a bed of length LMF. And then after that we have dP, which is the average diameter of the particles, which we need to know. We also have the shape factor, which is just a factor that is given or in the problem statement, or it's found in tables such as 3.1 and 2 in Genopolis. And it basically just accounts for the irregularity of certain particles. We also have rho, which is just the fluid density. We have rho p, which is the particle density. We also have the Reynolds number, which has been talked about a lot, and the equations given, and it basically helps describe the flow, and it'll help you solve problems for this topic. So specifically, we're going to talk about pressure drop minimizing fluid velocity. So you want to know the pressure difference that will make the fluid velocity the minimum. And for that, you're going to have to set the pressure force upwards equal to the gravity force downwards, because you want them to be equal in order to find the minimum velocity. And that's given in this equation here. And then using this equation, and also an equation that David derived to get delta P, that I don't really have time to go over, you get this long equation where Reynolds number shows up twice, which is why Reynolds number is pretty important to this problem. And then furthermore, doing some algebra and plugging in the simplification made by researchers Wen and Yu, that for a Reynolds number greater than 0.001 and less than 4,000, this term equals 1 over 14, and this term equals 11. Then you get this more simplified equation that is much easier to use. And to further the understanding of this topic, we're going to do an example problem, which can be found in Genopolis 3.1-6, part B and C in particular. And so if you're given all of these parameters, you want to find the pressure difference and the minimum velocity needed for the fluidization. So in order to find the pressure difference, you use step 1, which is use equation 2 to calculate delta P, which is pretty simple. You just plug everything into delta P, and then you get 0.0978 times 10 to the 5 pascals. But for step 2, you then use equation 3 to find the Reynolds number, or you can use equation 2 and use a solver, because this has RE twice, so you have to use a solver. But if you do either of those ways, you just plug it in and you get the Reynolds number of 0.07764. And then finally, you use that Reynolds number, you use the definition of the Reynolds number, and just plug in everything and solve for VMF, which is you eventually get 0.004618 meters per second, which is the minimum velocity needed to fluidize the particles in the packed bed. So I hope you learned something, and thank you for coming.